Hi, this is Dr. Goldstein, and I am going to talk to you about continuity. So the idea behind continuity is that a function is continuous if you can draw its graph. The function is continuous if you can draw its graph without picking up your pencil. So if its graph has no breaks, holes, or jumps. So it's a very visual description. You can look at the graph of a function and determine whether it's continuous, but in mathematics we really don't like to work from pictures unless we really, really have to. So we have the formal definition of continuity that says a function f is continuous at the point x equals c, and that's what we're defining, is what it means to be continuous at a point, if the limit as x goes to c of f of x is equal to f of c. So looking at this really means three separate conditions that you have to satisfy. So we have three separate conditions. One, the function has to be defined. At x equals c. And this really is so that we can write down f of c and have it make sense. So we can write f of c and it makes sense. The second thing is that the limit actually has to exist. So the limit must exist and be finite because 3, we want it to equal the value f of c. So the limit is equal to the value f of c. So there's really 3 different things. Your function has to be defined. Your limit must exist and be finite because you want it to be equal to the value of the function. One thing that I like to tell people about continuity, about this limit, is that these are the boring limits. So note, these are the boring limits. Because what this definition is saying is that to take a limit, I can just plug in c. To f of x. There's nothing interesting going on. It's just great. If you want to know what the limit's equal to, you just plug it into the function and you get the right thing. So, in a sense, a function being continuous at a point means that there's nothing interesting going on at that point. There's no breaks, there's no holes, there's no jumps. So let's look at an example, a nice simple example to illustrate this. So let's look at the limit as x goes to 1 of 2x plus 1. So this is a nice linear function. And I've drawn part of its graph down below, and you should know what a linear function looks like. It's just a line. It goes on forever. And so you think to yourself, yep, there's no breaks, there's no holes, there's no jumps, so that should be continuous. So what I should get when I take this limit is what I get when I plug 1 in. I should just get 3, because this should be continuous. So because we should have the limit as x goes to 1 of 2x plus 1 equal to 2 times 1 plus 1, which is 3. And we can verify this visually on the graph if we plug in x equals 1 and we go over to the line, and then we map that over to its y value. Yep, it looks like when I plug in 1, I end up getting y equals 3. Another way to think about this conceptually is what happens to 2x plus 1 as x gets close to 1. 2x plus 1 is going to get close to 3 when x gets close to 1. So notice we do have all three conditions. So 1, 2x plus 1 is defined when x is equal to 1. 2, the limit exists and is finite. And 3, the limit is equal to the value of the function. So we have all of those things. 2x plus 1 is defined. The limit exists and is finite. It is equal to 3. And the limit is equal to the value of the function. We do have the limit as x goes to 1 of 2x plus 1 equal to 2 times 1 plus 1. Great. Again, these are the boring limits. A function is continuous does not give you an interesting limit. So let's look at some pictures of things that go wrong with continuity. So these are some non-examples. These are a little bit more interesting. So here in this picture, whatever function we have here up at the top, we have some function f of x. And here when we look at this limit, we're looking at x equals c. The limit as x goes to c of f of x is equal to whatever value L this is. So here, if we go over and we map up and we map over, we get some value L. But what we notice in this picture is that f of c is undefined. So we are missing condition 1. And 3, technically, because if the function isn't defined, the limit can't be equal to the value of the function. So this is one picture of something that can go wrong. Down below, we have another picture of something that can go wrong. We have the limit as x goes to c of f of x is still equal to this value L. So if I take x equals c and I go up like this and I go over here, that's still some finite value L. And I also have that when I plug c in, I get some value out. So f of c is defined. And so we can see that. And again, if I plug in my c and I go up here, and then I map it over to the y-axis, that's my value f of c. I get a value out. So here's my f of c. But what we're missing in this picture is just condition 3. Since L, the value of the limit, is not equal to f of c. So both of these types of discontinuities are what are called holes or removable discontinuities. So these are holes, or more technically, removable discontinuities. So these are one type of discontinuity. Here's another example of a different type of discontinuity. So in the top picture, if I have my function f of x graph, that looks like a piecewise defined function. And what we see here is that the limit from the left, as x approaches c from below of f of x, this is equal to some value L1, where here, if I go here and I map over, I end up with some value L1. And on the other hand, if I take the limit from the other side as x goes to c from the right, I end up with some other value L2. So I go up, let's see, and I map that over. And here in my picture, there's L2. And so since we have different limits from the left and the right, the limit as x goes to c of f of x, the two-sided limit does not exist. This is because L1 is not equal to L2. The right and the left limits are not the same. So here, this function is not continuous at x equals c because we're missing condition 2. This is what is called a jump discontinuity. And you can see that the function jumps. The last kind of discontinuity that's pictured here in this bottom picture, so again, if I have this function f of x, we can look at the value of the function at c, and you say, oh, yeah, that's not defined because it goes off to infinity. I can't actually plug in c. So f of c is undefined. In a function, this is what it would look like if you ended up dividing by 0. You'd have this vertical asymptote. So we're missing condition 1. And also, the limit as x goes to c of f of x in this picture, this is infinity, so technically this limit doesn't exist. So this is not a finite value. So for the purposes of this definition of existing, our limit does not exist. So again, technically, the limit does not exist. We still say that it's equal to infinity, but technically this limit doesn't exist because it's not equal to a finite number. So here we're missing condition 1, we're missing condition 2. And if we don't have those two conditions, we also can't have 3. And same with the previous example too. If the limit doesn't exist, we can't have condition 3. So this last type of discontinuity down here is what's called an infinite discontinuity. And so this is the type of discontinuity that we get whenever we have a vertical asymptote. So the term infinite discontinuity is actually synonymous with vertical asymptote. It's just specific to when we're talking about discontinuities. So that is the idea behind continuity, and the best way to understand continuity is to actually understand what happens when you have discontinuities when the conditions for continuity fail.